I'm Aparna Prabhu. I'm a senior engineering manager in DigitalOcean for storage and platform engineering, and this is my teammate Saubhik. He is a gRPC aficionado. So we'll get started. Quick look at our agenda. So I know this is an intermediate talk, but for the sake of inclusion and to cater to every kind of audience that's gathered here today, and probably who'll look at this later, who'll look at this recording later, I'm going to touch upon briefly a little bit about the basics of gRPC, and then I'll hand it over to Saubhik to do a deep dive of gRPC at DigitalOcean, where we tried using the vanilla version of gRPC, but spoiler alert, it did not scale as we had hoped. So the rest of the session is going to be about that, how we've implemented DORPC, and finally EDS is our endpoint discovery service, and DOCC, which is our own custom Kubernetes platform on which we're running many microservices. So Saubhik will go into numbers, the scale, and that's what this story is all about. All right, so like I said, quickly touch upon the basics. RPC, I don't think anybody here does not know what RPC is, but the name is pretty self-explanatory. RPC is a remote procedure call. It's the idea that, or it's the technology wherein a program running on one machine can call a function which is running in another program, most likely in another machine. As simple as calling sum of A comma B, and it all feels local. That's the magic of RPC. Just to give you a quick analogy, it's like your services having a phone book, which is your DNS service, in our case, DNS discovery service, which is in our case their EDS, and making calls over the network. Okay, like remember the good old days where we had a telephone book and then we can just make a call. It didn't matter where the person was, right? It was all like pretty seamless. So that's how RPC is. It makes remote calls, no matter where the function is running, seem like local. If all that is so magical and hunky-dory, then why did Google come up with gRPC? Why did Google themselves have been using RPC, their internal architecture, but in 2016, why did they come up with gRPC? What was the need to do that? Mainly two reasons. One is HTTP2, and the second one is protocol buffers. Let's talk about HTTP2 first. The need to move from RPC to gRPC was primarily driven by the need for speed, and gRPC is driven by HTTP2. Back in the day, not sure if there is anybody here who's been working in the industry for like 15 years or more than that. It used to be all HTTP1. So how HTTP1 worked was every request opened its own TCP connection, and the response to that request had to be received before we move on to the next request. So it was three-way. Okay? It was very bulky, and as you can imagine, it was very slow. So this had to be fixed. Sometime down the line, they came up with HTTP 1.1. I don't remember the exact timelines, but the biggest thing that HTTP 1.1 brought in was the concept of pipelining. Okay, I'm not going to go too much into the details of pipelining, but HTTP 1.1 also had its own issues. HTTP 1 was a lot more recent. HTTP 1.1 is a lot more recent. HTTP 1 was like, I'm talking about 90s. Okay, but then HTTP 1.1 also had its fair share of issues. So then they came up with HTTP 2. So in HTTP 2, what happens is single TCP connection is opened and multiple requests can flow through it through this concept called streams. Streams was introduced in HTTP 2. Streams are independent of each other, so they don't have to wait for each other's responses. And it's also like small packets, so it was faster. Okay. And another thing is whenever the server had any updates, it could push these updates to the client without the client having to poll. So that's what I mean by push capability. So HTTP 2 was revolutionary. Of course, now we have HTTP 3, but then I'm not going to go into the details of that in the interest of time. That is how HTTP 2 kind of solved the speed problem. Another thing that I want to touch upon is protobuf. It's not just about speed, it's also about efficiency, right? I feel a little like I'm telling a story, but yeah, that's okay. Technical heavy lifting will be done by Saubhik. So Again, to quickly go down the memory lane for protobuf. Back in the day, we had to, before all this protobuf, HTTP2, all this came into the picture, we had to write by hand each HTTP request. We had to construct REST handler manually, okay? And not only that, once everything was in JSON or XML. You all have seen JSON files, right? It's very bulky, lot of data. And then we had to manually serialize it. Like we literally had to write code on both the client and server side to serialize it and deserialize it. It was a lot of effort, okay? Not funny looking back at those days. And it's not hard to guess that anything that has so much of manual intervention is naturally more error prone or buggy, right? So 3 issues. One is manual serialization and deserialization, bulky because of JSON and XML. And another thing is, if I have a program written in Java and Saubhik has something in C++, how do you make them talk? How do you make them communicate? This was again not at all easy back in the day. So our systems and our architecture was not platform agnostic. It was not language agnostic at all. So, it's a lot of work over and like you have to literally like, you have to reinvent the wheel every time you have to make some changes. It was very hard. So enter protobuf. So how did protobuf address these issues? So I'll tell you at a very high level again. We have something called a proto file. Think of it as it's like a translator basically, which ensures that everybody understands the same language and it is strictly typed. So people know what to expect. Client knows what to expect from the server and vice versa. And most common programming languages, be it Rust, Java, Python, Golang, all of them understand protofile. So you can write your programs in one language, have a protofile, and somebody else who wants to talk to your code can do so easily because you all are sharing the single source of truth, which is your protofile. So that is how this whole language agnostic or platform agnostic problem was solved by protobuf. Now, what is the second thing that I spoke about? Serialization. Protobuf takes care of serialization inherently. As a developer on gRPC, chances are you don't have to look at the code that serializes and deserializes. It is as simple as function call. So developers are abstracted from all that under the hood things. And the third thing is bulkiness, the third issue that I spoke about. Remember earlier in the slide I talked about JSON and XML. Let's get rid of that. Who uses JSON and XML for inter-service communication, right? So protobuf has this really cool binary encoding format where the messages are highly concentrated and reduced in size. So just to give you quickly an analogy that everybody can relate to, it's like zipping files. So what happens when you zip files? Their size is reduced. And when their size is reduced, it's easier to transport them. Automatically it becomes faster and it becomes more efficient. So that is how protobuf increase the efficiency. Ideal is the protofile that I was talking about. And then you have command line tools to generate client and server code. I'll quickly show you in the next slide how this happens. So this is a very summarized view. Pretty much the same thing happens at the client and server side. Your application talks to its stub. Stub is basically its version of the code that it can understand, which in turn talks to the gRPC library, which is sitting on top of HTTP2, and finally your transport layer. Transport layer is something that is common to all architectures, right? So this guy is the client. He has to query something, so he'll send it. It goes to the gRPC client stub because this guy can only understand the client stub. Client stub he's talking application's language, whatever it is. And then that goes to the gRPC library, and finally when this is converted back using the gRPC library, they all share the same source of truth. So the application running on the server can understand what the client is saying, process it using application logic, return the output, and it will follow the same path. Okay, this efficiency, speed, things like this are very crucial for cloud service provider like us. We are DigitalOcean. We are similar to your GCP, Azure, AWS. We have most of the top services used by all these hyperscalers. And for a cloud service provider, things like availability and reliability, this is our bread and butter. These are not things that we just talk in a meeting room and then forget about. Our life revolves around reliability and availability, which is why we chose gRPC and modified it to make it DORPC. And I'll now hand it over to Saubhik so that he can do a deep dive and cover the main part of this talk. Over to you, Saubhik.
Before we move to how we did DRPC, some scales that is we are running the DigitalOcean at, and that numbers are not exhaustive. I just spoke to one of my delivery engineering team guy and he gave me some numbers. 4,000 unique services are running at any given moment. More than 25,000 service of instances. It's based on Kubernetes, so you can say it's a service of pod, or you can say 1 million requests per second internally happening. Sub 100 millisecond latency we are providing to the customers, and internally it is way more or less like sub 10 millisecond latency we have. 15 to 20 gigabytes of data moved per second. 99.9% of services that we have inside the DO is communicating using gRPC. Only the couple of like 0.1% services that is client facing is using the JSON or REST architecture because client needs in that fashion, but 99.9% services that we have at DO using gRPC or DRPC, you can say. Quickly, hello world. We'll write hello world of gRPC and then move, evolve, and how it is done using the DRPC that is done at DO. Okay. Simple application, chat app service that has two RPCs, get all chats and then chat. So get all chats is a simple make a request, get a response, and chat is a bidirectional stream where you can send multiple messages and the server can send you multiple messages as well. Monorepo. So I'll quickly touch on this aspect. So monorepo, there is one more talk. I can refer if you want. You can come and after this talk. That talks about how you solve a problem to keep, where do you keep your proto files at scale, and then you solve that particular problem of keeping your protos and sharing your protos. The best part for DO, 99% services lives in the same monorepo, except few very intriguing services written in Rust or some other languages. That is outside the monorepo. Everything is inside the monorepo and just import away. So you can just simply import and then use the protofiles of the different services. Let's say virtual machine service wants to talk to volume service. They can simply import their protos, generated code. Quickly, the DRPC. DRPC is nothing, a framework created on top of the gRPC. This is the standard. Any production service that goes into the DO has to have, if it is based on gRPC, it has to have this DRPC, using the DRPC. They cannot create, why would they want to create? They are getting a lot of things out of the box. We'll cover one of them one by one. Out of the box, they are getting the structured logging, they are getting tracing, they are getting matrix, P50, P99, these all things they are getting out of the box just by using the DRPC. They don't have to configure anything. So error count, user agent, bunch of other things as well. This is not exhaustive list again, but few other things just to give you the flavor like what you're getting out of the box. Interceptors is the key, how we have solved these things. gRPC gives you a really nice way to extend. It is really extendable. You can write your own interceptors in any form of matter, and then you can extend your features of the gRPC that has been given to you. So same, we are using the DRPC uses heavily, depends on the heavily of the gRPC interceptors. Like context logging, any network calls that comes into the DO comes to the edge gateway. Edge gateway adds a bunch of things like request ID, user agent, user ID, all those things. I'm talking in terms of, we are using Go, everything Go. So in Go, if you are using Go, you know there's something called context and you can share things in the context. So the whatever the context we are getting down the line, you'll get all those things added automatically in your context in your gRPC call. So context logging you're getting, that is automatically added by the DRPC. Tracing you're getting, trace supports OpenTelemetry. I think there's one talk happened before the day that was talking to OpenTelemetry. Metrics you're getting, like how many seconds particular request response took, how many total requests that you have, how many failed, like the codes and all. These all you're getting out of the box. You just have to give your service name and you can query the things from your centralized metric server. Default provided client. So by default, if you have vanilla gRPC, you know that if you're creating a client, you'll have to provide your own connection stuff. Here, DRPC gives you automatically generated code that you can simply use to make a connection to the client. So whatever code you have generated using gRPC, it will have a default provided client. I'll show you one code. That is how it looks like. That is the new chat service dialer that we have. You can simply use this chat service dialer. You can provide some OPTs, that is DRPC OPTs, we'll cover some OPTs down the line. But it is again not required. You can simply use that and dial or dial raw. It will automatically be taken care. You don't have to worry about anything else. Cool. More like you can add some retry middleware. You can add some client timeouts. You can add some error handling and bunch of other OPTs that you can add. That is provided by the gRPC itself. TLS everywhere. So our Kubernetes implementation is based on the DOCC, a framework developed on top of the Kubernetes called DOCC. Anyone, like again, more than 95% services using DOCC to deploy their services in production. Why to use? They gives you a lot of things out of the box. It is beyond the purview of this talk, but we are using DOCC. And if you are using DOCC, you just have to do auto TLS true. And just by adding auto TLS true, you are now inside a TLS arena. So just add auto TLS true and just add your client SAN in the manifest file that you're going to write for the DOCC, and will automatically give you the TLS features for you. We'll see some of them down the slides. So here is an implementation. Yeah, we are writing in JSON. Manifest file is written in JSON for DOCC for some reason, I don't know. Everyone is moving to YAML, and we are moving to JSON. Auto TLS true. This is the thing that is the key that you have to do. And you'll have to add a SAN that I have not added here, but if you want to communicate something, you'll have to add SAN. Client balancer. So you're also getting the client load balancer. There is again a talk in the gRPC. I can refer if you want. Client balancer is implemented out of the box. I think by default it supports round robin, plain round robin, but you can use weighted round robin or other custom load balancing as well. So it is provided you out of the box. The plugins provides you can see in the code. You just have to write the balancer at the end. You can see the plugin. That is the way you use the gRPC thing. We have created shell script, but gRPC is a framework. You just add a balancer, and the code for the client load balancer will also be generated. That is how the client load balancer looks. Too much to process, but you can get this PPT, I think. We have a service called EDS, that's the endpoint discovery service. And endpoint discovery service works like a DNS of how the DNS works with the normal vanilla gRPC, okay? So what you do, you just point your production EDS endpoint and then give your service name and the preferred region. And then you can simply provide this address of the EDS to the dialer. You can see the connection factory, and we're providing the address dial raw. And then at the end, we are seeing the new direct load balancer and providing the client factory. It will automatically, you can take this client balancer and provide the new chat app service dial balancer that we have seen earlier. And it will automatically create all the connections for you, and then automatically load balance according to the balancer that you have selected. I have not selected anything, so it is going to fall back to the normal round robin. MTLS config is as simple as adding just a config, just annotations. So simple config, just add MTLS true. That is provided by the gRPC auth mode. You can simply add MTLS true, and then just by adding the MTLS true, your gRPC RPCs are now MTLS compliant. You have to do a couple of things. I'll get back to that, but this is as easy as just you have to add this MTLS true. MTLS auth interceptors. So once you have made your services to be MTLS true, anyone that lives in your own, that's a common repository, but lives in your own directory, and you are the owner of the directory, so you can decide who has the access to particular RPCs or not. So in here you can see I have added a string where you can add your service domain name. You can see this, you just have to add an interceptor, and that is also provided by the gRPC team and IM team. IM team implemented gRPC, and then they have provided a thing you can just add, and then it will automatically, whatever the service you have mentioned here, they only have the access to your RPCs. RBAC is also similar, you can see. It is also provided by the auth. You can simply say what is the permission you want, what is the required permission you want. I put here droplet create and BBC update. That's not needed for the chat, but you can, and there's a super user C. So you can do these things, and you will automatically get RBAC. And then you'll have to have interceptors at your server side that you can simply create. There is a policy engine client we have created. This is open policy engine, open policy agent engine based. And then you can simply provide that, and it will automatically check your certificate. Certificates are automatically injected in your services when you create a DOCC service with the MTLS true, when you auto TLS true. So it will check your certificates automatically. Cert checker tool we have, and then if you have the permission, you will go through, and then you can access the RPC. RBAC client looks similar. You just have to use the policy engine client provided, and it will automatically check your certs and then give you the access if you have the access. This is the EDS. EDS is a very generic service that we have created at DO. You can give the service name, and there are, as I mentioned, like more than 4,000 services are running. So you can just give the name and the region where you want to connect, and this EDS is automatically going to give you all the addresses that it has of that service. So you can simply connect. And with the gRPC, it works like out of the box as a DNS, so that is also helpful to you. And this is how it looks. There is an EDS URI package we have created. You can use this and form your EDS thing. And there is a, you have to import, this is an EDS resolver. There's a bunch of init functions. I have seen the code shown the code in terms of Go, but I think you get the idea. Cool. This is all comes together. DRPC, DOCC, and bunch of other things all comes together and scales infinitely. That's the topic of our talk. And we have not seen any issues so far, so I think it is going to scale further. That is it. Monorepo is the savior, believe me. If you are making some really big service, please consider. I was a big, out of time, but I was a big critic of the monorepos when I heard like Meta uses monorepo, like big monorepo, hundreds of or tens of millions of lines of code remains in the same repository. I was really critic, but when I work myself, I'm a big fan of monorepo.